Welcome back. In this video, we look at a model that has proved to be very useful in many NLP applications. The encoder-decoder architecture, also called a sequence-to-sequence model. Take, for example, a machine translation scenario in which English is being input into the system, and the goal is to have Spanish as the output. The source language goes through a neural network that encodes the input data into some intermediate state, typically a tensor representation. Then this intermediate representation goes into another neural network, the decoder, to output data in the target language, Spanish, let's say. The advantage of decoupling the encoding and decoding is that the source language inputs don't have to be the same length as the target language. For example, in English we may have a sentence with 3 tokens, how are you, which could be translated as 2 tokens in Spanish, ¿cómo estás? Both the encoder and the decoder are separate neural networks, usually constructed out of LSTM or GRU layers. The intermediate state here acts as the initial state of the decoder. The decoder learns to predict the next token, offset by 1 time step in the future. This is referred to as teacher forcing in the literature. This notebook in the GitHub is an example adapted from a blog post by Francois Chalot. It uses a data set of English-French pairs of sentences, which I downloaded from here. And by the way, this has pairs of many different languages. One interesting feature about this notebook is that it learns character by character instead of token by token. So the data looks like this. Each line is an example in a CSV file where we have the English first, followed by French in this case, followed by some other information. The first step after reading in the file is to generate a list of input text and a corresponding list of target text. Meanwhile, it will gather a set of input characters and target characters. Here's just a few parameters that we'll need later for training. Now we need to vectorize the data. Then we're going to create sparse matrices, one for the input here to the encoder, another for the input to the decoder, which will be filled in by the encoder, and then our final decoder output, which will be filled in eventually by the decoder. Next, we're going to set up the encoder. The encoder will have an input shape of 71 because there were 71 unique tokens in our input data. After the inputs, we have an LSTM layer of dimension 256. Then we have our outputs. The encoder will return state H and state C. Whereas a regular RNN just has a hidden state, the LSTM is more complex and also has a C state, the state of the cells. And this mechanism is what allows both memory of prior states and forgetting of prior states. And we'll package those together into the encoder states here. Now we're setting up the decoder, which takes as input the encoder states that we had. Then we'll have a dense layer for outputs with softmax activation. In other words, over all the possible output tokens, this will determine the most likely one. We set up our model with our inputs and our outputs, compile, and then fit. Here I save the model in case I wanted to use it in another notebook, which actually I didn't. And this took about 22 minutes to train. The next part of the notebook sets up an inference engine that we could use to put some input in, encode it, run the decoder, and get our target output state. In here we're using that inference engine that was built on part of the training data and outputting the input mapped to the output. So what did this sequence-to-sequence model really learn? Honestly, it simply learned to map input phrases from one language to another. Basically, it memorized that mapping. The fact that it did it on a character level instead of a word level is a further indication that this is not at all how humans process language. We actually vary our output. We might say things in English, for example, "How have you been? How are things?" or countless variations. In contrast, this learned input-output pairing seems quite robotic. Nevertheless, I wanted to present this very simple example and discuss sequence-to-sequence models because they're pretty hot topics in NLP right now. In addition to being used for machine translation, they're also used for question answering systems. This is an open research area, so we'll have to see what improvements come to this in the future to be able to build viable real-world systems.